Welcome back to TalkTensors.
Yeah, it's great to be back.
Today we're going to be taking a deep dive into a paper that really has us buzzing.
Yeah, it's a pretty exciting one.
Yeah, and the title is quite a mouthful. It is Agent Models, Internalizing Chain-of-Action Generation into Reasoning Models. So, catchy title. But, the paper itself points to a pretty big shift in how we're thinking about building AI.
Right.
We're moving beyond these chatbots that can just, have conversations. We're moving beyond just reasoning models to truly autonomous agents.
Yeah. I mean, it's the dream, right? Mm-hmm. We've always wanted to get to this point where the AI can not only reason, but also act on that reasoning. And this paper really tackles, I think, the core challenge there, which is, how do you get these models to decide for themselves when and how to use tools without needing us to explicitly prompt them every step of the way?
It's interesting, right? Because we've seen this huge progress in language models. And, we've had systems like React, which allowed models to reason and then act using external tools. But they still needed us to kind of guide them, like, okay, now use a search engine or now, access this database.
Right. Yeah, there was still this element of like a human in the loop, kind of orchestrating the workflow.
Right.
But now we're talking about models that can have that aha moment themselves. They're reasoning through a problem and they realize, oh, I need more information. I need to look something up.
Yeah, exactly. And I think that's where these large agent models, or LAMs, as the researchers call them, really come in. They're learning to internalize that decision-making process.
Right. And it's a natural progression, right? We've seen how reasoning models evolved. Mm-hmm. Initially, we had to prompt them to show their work, those chain of thought prompts, to get them to explain their reasoning step by step.
Right.
And now, with enough training data, they can generate those steps internally.
Yeah.
So this paper is basically saying that we're seeing a parallel evolution with tool use.
Yeah, makes sense.
Instead of prompting them to use a tool, these LAMs are learning to internalize that decision.
Yeah, and they call it chain of action. So we have chain of thought for the reasoning, and now we have this chain of action for deciding when and how to act.
Exactly.
So what is this AutoCoA framework that they introduced?
So AutoCoA is essentially their proposed solution for training these reasoning models to become more agentic.
Okay.
And it's a pretty clever two-stage process. The first stage is supervised fine-tuning, which, is a common technique in machine learning.
Right, SFT.
Exactly. And then they follow that up with reinforcement learning, which is really where the agent learns to optimize its actions based on feedback from the environment.
So it's like they're first giving the model a strong foundation in how to reason and act, and then they're letting it loose to kind of figure out the best strategies on its own.
Yeah, and I think one of the key insights here is that they're not just training the model to use tools, but they're training it to decide when to use them.
Yeah.
And that's a really crucial distinction.
Yeah, that's a good point. So let's dive a bit deeper into the paper itself. They start off kind of setting the stage, right? Talking about how AI has progressed from these chatbots to reasoning models.
Right. Yeah. They talk about OpenAI's 5 stages towards AGI. Mm-hmm. Started with the chatbot, then the reasoner, then the agent.
Okay. So the agent is like the next level.
Exactly. It's where the model becomes truly capable of interacting with the world and achieving goals. Mm. And they highlight OpenAI's own work, like Operator and Deep Research, as examples of this progression towards more agentic AI.
Right. Yeah. And they also make this really interesting analogy to, the history of reasoning models themselves.
Right. They talk about how we used to have to handcraft rules for everything. Yeah. And then we moved to this more data-driven approach, where models could learn from examples. And they argue that we're seeing a similar shift with tool use.
Right.
From explicitly prompting the models to use tools, we're now moving towards training them to figure it out on their own.
Yeah, and this idea of internalizing the chain of action is really central to that.
Absolutely.
Okay, so they then define what they mean by an agent model, right?
Yeah. They get into the nitty-gritty of how these models work. And for anyone who's really interested in the technical details, I encourage you to check out the paper itself. But at a high level, they describe an agent model as a generative model, kind of like the language models we're used to. But it's trained specifically for tasks that require using tools to interact with the environment.
Okay.
And they formalize this interaction as a partially observable Markov decision process.
POMDP.
Yeah.
I think I've heard of that. But can you kind of explain it in simpler terms?
Sure. So imagine you're the agent.
Right.
You have a task to complete. but you don't have all the information you need up front.
Okay.
So you have to make decisions based on what you know so far and the feedback you get from your actions.
So it's like navigating a maze where you can only see what's right in front of you.
Yeah, that's a great analogy. And at each step, the agent has to decide what to do next. Should it think more? Should it take an action like using a search engine? Or should it provide an answer based on what it already knows?
Okay.
And they represent these different choices as different types of tokens. So you have a thinks a token for the internal reasoning steps, an O stands token for deciding to use a tool, and an answers token for, well, providing the final answer.
So it's like the model is generating this internal script of thoughts and actions.
Exactly. And the key thing is that the decision to take an action, to use a tool, comes from the model's own internal logic, not from an external prompt.
Yeah, that's a big difference from how we've traditionally approached these things. So what are some of the challenges they faced in training these agent models?
Well, one big challenge is balancing the ability to reason effectively with the ability to take useful actions. If you focus too much on training the model to act, it might forget how to think deeply, or it might start taking actions at inappropriate times during its reasoning process.
Right. You don't want it just jumping to conclusions without thinking things through.
Exactly. And then there's the challenge of managing the interaction with the external environment. Using tools like web search can be expensive, both in terms of compute resources and time.
Yeah, that makes sense.
Plus, the real world is messy and unpredictable, which makes training more complex.
Right. Like the internet is constantly changing. So how do you train a model to use a tool that's constantly evolving?
Yeah, that's a really tough problem.
Yeah.
And the paper actually mentions OpenAI's deep research as an example of this. They had to deal with the costs and challenges of using a search engine that's constantly indexing new web pages.
Right. So this AutoCoA framework, how does it address these challenges?
Well, like I mentioned, it's a two-stage process, SFT and RL.
Okay.
And they actually break down each stage further into substages to kind of gradually build up the model's capabilities.
So it's like a step-by-step process.
Exactly. So in the first stage, the SFT, they start by training the model on, carefully crafted data. They use the HotPot-QA data set for this.
Which is?
It's a question answering data set where the questions often require finding information from multiple documents.
Okay.
So it's a good test for an agent that needs to use tools to find information. And they actually generated 3 different types of data for this SFT stage. They have pure chain of thought data, where the model is just reasoning without using any tools. Then they have chain of action data, which includes examples of the model using a search engine and observing the results. And then they have this really clever type called QT plus A data.
QT plus A?
Yeah. And this is where they use contrastive learning to teach the model when it's beneficial to use a tool versus when it's not. So they're showing the model pairs of examples. In one example, taking an action, like performing a search, leads to a better outcome. And in the other example, either not taking an action or taking a different action leads to a worse outcome.
Oh, I see. So it's like they're highlighting the good decision-making pathways.
Exactly. And they use a special loss function, contrastive loss function, to encourage the model to learn from these examples.
Okay. And then what happens in the second substage of SFT?
So in the second substage, they shift the focus to teaching the model how to take an action.
Okay.
So they train the model on these full interleaved sequences of reasoning and action, but they mask out the feedback from the environment when they're calculating the training loss.
Why do they do that?
Well, the idea is to get the model to learn the mechanics of taking an action, choosing the right tool and the right parameters without being influenced by the result of that action.
So it's like focusing on the form first before worrying about the content.
Yeah, exactly. It's about getting the how right before fully integrating the what happened next. And then in the third and final SFT substage, they bring back the environment feedback. So now the model has to predict not only what action to take, but also what the response from the environment will be.
Oh, okay.
And this is really important because it allows the model to build an internal world model.
A world model.
Yeah, it's like the model's own internal representation of how the tools work and how the external world responds to its actions.
So it's like it's learning a simulation of the environment.
Exactly. And that can be really valuable for efficiency because it means the model doesn't have to rely as much on those expensive real-world interactions during training.
Yeah, that makes sense.
And then they move on to the RL stage, which is all about optimizing the agent's behavior based on rewards.
Right.
So they use this technique called Group Relative Policy Optimization, or GRPO.
GRPO?
Yeah.
And what kind of rewards are they using?
Well, they have a pretty straightforward reward system. The model gets a high reward if its final answer is correct, and if it follows the expected format, using those async tags appropriately.
So it's like rewarding the model for both being right and being well-behaved.
Yeah, exactly. And they also break down this RL stage into two parts. First, they train the model extensively in a simulated environment. And this is where that internal world model comes in handy. The model can use its internal simulation to predict the results of its actions, which allows for a lot of experimentation without having to actually interact with the real world.
So it's like a safe space for the agent to learn and make mistakes.
Yeah, exactly. And then once the model has learned some good strategies in the simulated environment, they fine-tune it by actually letting it interact with the real world.
Right. So it's like taking off the training wheels.
Exactly. And this two-part approach is really effective because it allows them to strike a balance between efficiency and realism.
Yeah, it seems like a pretty clever way to train these agents. So how do they actually evaluate the performance of their AutoCoA framework?
So they tested their models on a variety of question-answering data sets. Some of these data sets were single hop, meaning the model could find the answer with a single search query, and others were multi-op, meaning the model had to perform multiple searches and combine information from different sources. And they compared their AutoCoA trained models against models that couldn't use any actions at all, and also against models using more traditional agent workflows like React.
Right. So how did the AutoCoA models stack up?
Well, the results were pretty impressive. Across all the data sets, the AutoCoA models consistently outperformed both the non-agentic models and the React-based models.
Wow.
Yeah, it was a pretty significant improvement. And they also found that separating the training of when to act and how to act in that SFT stage was really beneficial.
Right.
So those carefully designed substages really paid off. And interestingly, they found that just applying reinforcement learning directly without that strong initial grounding from the supervised fine-tuning didn't lead to much improvement.
Okay.
So it's really the combination of the SFT, including that internal world model, followed by the RL in both simulated and real environments, that gave them the best results.
Yeah, that makes sense. It's like building a house. You need a strong foundation before you can start adding the fancy stuff.
Exactly. And they also analyzed how well the models could handle tasks that required longer sequences of reasoning and action.
Okay.
And again, the AutoCoA models performed much better than the models that hadn't undergone this specific training.
So they were better at planning and executing complex multi-step tasks.
Exactly. And I think that really highlights the power of internalizing the chain of action.
Yeah.
The model isn't just reacting in the moment. It has this internal understanding of how to break down a complex task into a series of smaller steps and how to use tools effectively to achieve its goal.
So what are the key takeaways from this paper?
I think there are a few really important points for our listeners to keep in mind. First, this idea of training models to decide when and how to use tools is really a game changer.
Yeah.
It's moving us towards a more autonomous and intelligent form of AI. And second, the AutoCoA framework is a really clever and effective way to train these agents.
And it's built on a lot of really interesting ideas like that internal world model and the simulated environment training.
All right. And third, the results they demonstrated are really impressive. They show that these large agent models have the potential to tackle really complex problems that were previously out of reach for AI.
Yeah, this is really exciting stuff. And it's great to see that researchers are making so much progress in this area.
Absolutely. And, the paper also talks about some really interesting potential applications for these agent models.
Yeah, they have this whole roadmap for how they see agents evolving in the future.
Right.
So what are some of the things on that roadmap?
Well, in the near term, they talk about things like more advanced robotic process automation, where AI can handle more complex and nuanced tasks. And then there's this idea of truly helpful personal assistants.
Right.
Assistants that are proactive and can work across different devices.
Mm-hmm.
They also talk about specialized domain analysts, AI that can leverage expert knowledge and tools in specific fields.
Okay.
And even coding agents that could potentially automate a lot of the work that software engineers do today.
Wow. So AI writing code, that's pretty wild.
Yeah, it's definitely a possibility down the line.
Hmm.
And then looking further ahead, they have these ideas for action executors.
Action executors.
Yeah. These are agents that can interact with a much wider range of inputs and outputs, potentially even bridging the gap to the physical world through things like IoT devices. So imagine an AI that can not only control your smart home, but can also learn your preferences and anticipate your needs.
Yeah, that's getting pretty close to sci-fi territory.
Right. And then they have this idea of insight seekers.
Insight seekers.
Yeah. These are agents that go beyond just answering questions. They can actually explore data, conduct experiments, and generate new knowledge on their own.
So AI scientists.
Yeah, potentially. It's a really fascinating idea. And then their most ambitious idea is this concept of an agent OS.
Agent OS.
Yeah. So imagine a fundamental software layer where agent models act as the central processing unit, tools of the software, and memory is seamlessly integrated.
So it's like an operating system designed specifically for agents.
Exactly.
Yeah.
And it would have all sorts of implications for how we interact with technology and how we think about AI in general. But of course, there are a lot of challenges involved in building something like this.
Yeah, I can imagine.
They talk about the need for unified representations for different types of data, tools, and memory. And they also raise the question of how we would design agent-specific instruction sets.
Agent-specific instruction sets.
Yeah, right now, most of these models operate on sequences of text tokens. But what if we could design a more native set of instructions, tailored specifically to how agents think and act?
Oh, I see. So it's like developing a new programming language for agents.
Yeah, potentially. And that could potentially unlock even more powerful capabilities down the line.
Yeah, that's a really interesting idea. So what are some of the real-world implications of all of this research?
Well, I think the potential impact is huge. We could see AI that can conduct in-depth research on its own, solve complex scientific or engineering problems without constant human guidance, or provide truly personalized support by understanding our needs and proactively taking action.
Yeah, and we already talked about the potential for automating a lot of tasks in businesses.
Right. And the idea of AI helping to write code could really revolutionize software development. It could free up human programmers to focus on the more creative and strategic aspects of their work.
Yeah, that's a really exciting prospect. So it seems like this research has a lot of potential to change the world in some pretty significant ways.
Absolutely. And I think it's just the beginning. We're going to see a lot more research in this area in the coming years, and I'm really excited to see what the future holds.
Yeah, I'm with you on that. And now, for our Novel Notions segment, this is where we like to take the research we've discussed and brainstorm some potential future directions.
Right. So building on this idea of the internal world model, what if we could extend it to simulate not just the tool's response, but also potential user reactions or feedback to the agent's actions?
Oh, that's interesting. So it's like the agent is not only predicting what information it will get from a search engine, but also how a human user might react to that information.
Yeah, exactly.
Yeah.
And we could potentially combine this with reinforcement learning techniques that incorporate simulated user satisfaction as a reward signal. So the agent would be optimizing not just for completing the task, but also for creating a positive experience for the user.
That's a really cool idea.
Yeah. And I think it could lead to much more helpful and less frustrating AI assistants.
Yeah. Right now, a lot of AI assistants can be pretty clunky and annoying to use.
Right. But if they could anticipate our needs and preferences better, and if they could learn to avoid doing things that we find frustrating, then they could become much more useful and enjoyable to interact with.
Yeah, that makes sense. And I think there's a lot of potential for this kind of technology in areas like customer service. Imagine a chatbot that can actually understand your frustration and try to resolve your issue in a way that makes you happy.
Exactly. And another potential benefit of this approach is that it could reduce the need for expensive real-world user testing.
Oh.
If the agent can accurately simulate how users are likely to respond to different approaches, then it could learn to avoid potential pitfalls and refine its strategies internally before it ever interacts with a real human.
That's a great point. So how realistic is it to think that we could actually build agents that can simulate user feedback this accurately?
Well, I think it's definitely a challenge, but I also think it's a challenge worth tackling. Initial simulations might be relatively crude, perhaps only capturing real user responses accurately, around 50% of the time. But as we gather more data and develop more sophisticated models of human behavior, I think we could see that accuracy improve significantly, perhaps even to the point where simulated feedback becomes a really valuable tool in the development process.
Yeah, that would be amazing. So it seems like there's a lot of exciting potential for this line of research. And speaking of exciting potential, what about that idea of agent-specific instruction sets?
Right. I mean, it's a really intriguing thought. And, moving beyond natural language as the primary interface for agents, it's like asking, could we develop a more fundamental way for agents to understand and interact with the world? And could that lead to more efficient computation and even more powerful capabilities? It's certainly a question worth exploring.
Yeah, definitely. So to wrap things up, it seems like we're on the cusp of a really exciting new era in AI.
I agree. And this paper, Agent Models, Internalizing Chain-of-Action Generation into Reasoning Models, is a really significant contribution to the field.
Yeah, it lays out a clear path towards building truly autonomous agents that can reason, plan, and act in the world.
Exactly.
So for our listeners, I highly encourage you to check out the paper itself and think about the implications of these advancements for your own areas of interest and expertise.
Yeah. And one final thought for you to ponder. As these agents become more sophisticated and autonomous, how will we need to rethink the fundamental ways we collaborate and share responsibilities with them?
That's a great question, and I think it's one that we'll all be grappling with in the years to come. So thanks for tuning in to Talk Tensors.
And we'll see you next time.
Bye.